Start now. This is just a mini lecture on glazing to give you kind of the fundamentals of the theories behind glazing. And I want you all to look this way, kind of keep it down. You can continue to work, but just make sure you listen and not make a lot of noise. So what we've got here is the formula for clay. And if you look here, then you have some similarities in the arrangements. It's not the same thing, but it's separated into parts. So we start with silica, which is your glass former, and put that over here. There's a couple of names for silica. It's not the only glass former, but it's the main one. So it's also called flint. And you can get flint from rocks, from sand. The easiest way for making glass is to say melt sand with something in it. You can melt it at high temperatures. It melts around, I believe it melts around 2,000 to 3,000. I can't remember if it's 2,000 or 3,000. But anyway, I think it's 3,000. So, and alumina so you can think about these in a couple of different ways, and these analogies are not my own; they're ones that I've come across. So your silica is sort of like your skin. So we can say this is the skin, and silica. And it's also like, if you were using the metaphor of a car, it would be the car. It would be the glass that you're making, the object. But to speed up the melting of it, you have a flux. And that's sort of like your blood that flows. And it also is the accelerant. So in terms of chemistry, you could call it a catalyst, because it makes other materials react. So sort of like the blood, and then the other one will be the bones. So what is the solidifier, or the braking, or the brake that puts on the brakes to the accelerator, the flow, the movement. So the bones is actually kind of interesting because bone ash is also sometimes used as an opacifier, so it has a place in glazing itself. We'll get to those in a minute. We'll keep the colorants and the opacifiers for later. So I can't tell you exactly what RO, R2O3, and RO2 mean, but obviously this is oxygen. It has 1, 2, and 3 oxygens in it. And there's always exceptions to the rules when you're talking about glazing. There are some exceptions to the rules. Another glass former would be so the main one for the stabilizer, or what I'm calling bones here, the thing that slows down the melt, is alumina. And if you look above, that's already the two basic minerals in clay: alumina, silica, and the other one is water. So you get oxygen from either of these. Aluminum hydrate would be, aluminum with a water molecule with it, I believe. I may be making some mistakes here as far as chemistry goes. The silica has oxygen in it, and the hydrogen. It stabilizes whenever it's combined with something. That's a stable form of it. So it combines with oxygen. But aluminum, another thing that also can stabilize is boron. But the odd thing about boron is a very versatile material. That's why it's used in so many so many glazes and so many frits. We'll get around to that in a minute, what a frit is. But it falls in this category with a stabilizer, but it's also a flux. It's also a stabilizer, but it's also a glass former. So lead's another one that's a glass former that is also, well, I don't know if it goes there, but lead is also a glass former. You can have a lead, but basically, well, it should actually go in the flux area, but there's often really high lead. Actually, lead is a flux, and it's used to make the lowest firing glass with silica. So it's like the oldest flux that we use. But usually, in most glazes, we use either a frit or a feldspar for a flux. And then there are a bunch of other materials. A feldspar or a frit. The thing about feldspars and frits is that they usually have both aluminum and silica in them. But they're a balanced way of adding materials so that you don't have materials that will leach out. It becomes a stable glass so you can control it easier in the mix. So there's also some natural frits, occurring frits, like one we use a lot is, which the mines may not last. They've closed the mines a couple of times until they realized a lot of potters would buy the materials even if they weren't pure enough for industry, and that's Gerstly borate. So it's a borosilicate flux. It's like an impure form of cobalt-bonite. And I don't expect you to remember all these, but the feldspars are either of potassium, calcium, soda, like either sodium. I should put soda. I should put sodium. Sodium, and there's other ones as well. Lithium. So sodium, potassium, calcium, and I'm trying to think. Strontium, barium, lithium. Some of these are like barium is poisonous, so you have to be careful with it, but it makes interesting glazes. And these are basically your alkaline earths or your salts. They're called salts and alkaline because they're sometimes called basic acids. So they're basic. If you know anything about chemistry, that means the acid is on one side, basics on the other, and they both can burn. Like acids, usually we think of things that will. So you have to be somewhat aware of materials. Like ashes is also another one that can be used. Ashes has all of these materials as well. It's sort of like, and it depends on the materials origins, like where it is, what kind of plant it is. But ashes will have sodium, calcium, potassium, and silica, and alumina in it. All of those things together. So it can be a glaze by itself. And some feldspars can make a glaze by themselves. What you usually want to do is add a little bit of clay as a binder to it. So clay will also give you alumina and silica. So we can put clay in both of these categories. Now clay can also be a colorant. So I can't write everything down here, but clay can, you'll notice that the molecule of clay has both alumina and silica, So it can be in both of these, but sometimes clay has high amounts of impurities, and so low fire clays can actually work as a glaze at high fire. So they can actually be in this column because they have flux in them as well. And so for colorants, what do you think? What do you think creates the colors in glazes? Yeah, but what chemicals? What kind of chemicals? I mean, you'll have trace minerals in clay and some of these others that can add a little bit of colorant to the piece. And this is by no means an exhaustive thing. This is just the beginning to get you to start thinking about what's in glazes. I have all of the glazes almost have the ingredients on them, so you can look at them and you can start thinking, well, that's got, you know, silica in it, that's got alumina in it, that's got the flux in it. So you can start thinking about basic glazes. So later, if you want to, you can start experimenting and making your own glazes in your own studio. So you need to start thinking about it. So colorants, where do we get our colors? Y'all, some of y'all are painters already, right? So where do the colors come from that you paint with? Think of the names of some of them. You got cadmium. Okay, cadmium is I believe is a metal. You got cobalt blue, right? The cobalt is also a metal. So what do you think? Where do most of the colorants come from? Your metals. So one of the strongest ones is cobalt. And cobalt will make mostly blues, but it'll also make purples and pinks a little bit, depending on how you use it. It can be a muted blue if you add an iron pigment to it as well, or like one way of modifying a blue so it's not quite as strong is by adding rutile, which is a titanium compound with iron in it. So rutile is another one. And titanium is a metal, but it's usually white, and it forms crystals. So there's a lot of other things that can happen to glaze. What did you say? Iron is one. You're right. Iron. And so this one makes a blue color usually, but it'll also make purples and pinks. So iron. What would iron? What colors would iron make? What do you think? When we see iron, what does it usually look like?
Brownish red.
It's a brownish red. So those are two colors. What? Gold? It's gold sometimes. So it's usually brown. You can also, at low temperatures especially, make a red. You can also have a reddish brown at high temperatures. It will also make black. So black colors, which the chalkboard is already black, but small amounts of iron, especially at low temperatures, can make yellows. And even at high temperatures, a small amount of iron can make a yellow, this wood yellow. But a lot of it depends on the chemistry of the glaze, and whether it's alkaline or basic, or even some unusual chemicals that will change the colors of that. But also iron will make greens. It will even make blues. So iron is one of your most versatile, but it also can be very subtle. Your browns and your blacks are not so subtle, but the other color, and your reds, your reduction reds at low temperature iron can be really bright reds. So it can make bright red colors, it can make dark colors, it can make like pale greens in celadons. Y'all know what a celadon is? Y'all seen like Chinese celadons? It's usually a clear glaze. It can be a somewhat opaque glaze as well, but it usually has a little bit of it usually has a little bit of gloss to it, but not always. Some celadons that are called celadons are not necessarily, but but they're usually a pale color. Now they call celadons, they have colored celadons for electric firing. So usually a pale, glassy color, somewhat opaque, but still with a little bit of gloss to them. And those usually are just a small amount of coloring. But in reduction, the traditional celadons in reduction are pale green or bluish green, made with iron. And you can create a bluish celadon by adding a little bit of cobalt to the iron. And most clays have a little bit of iron in them, so some of those celadons may have actually come from a clear glaze that the iron in the clay comes through at high temperature. So in reduction, small amounts of iron can turn green. So copper, nickel, chrome are other metals that can be used. So copper, what do you think the colors are that it is?
Red.
So you can get copper reds, but mostly in reduction. There is a way to get reds with copper in an oxidation atmosphere. And the difference between oxidation and reduction is relatively simple, even though it was hard for me to figure it out. And I know it sounds like Greek, probably to any of y'all, unless you know Greek. And then it sounds like some language that you can't speak. So reduction is when you're starving the fire of oxygen. It reduces the oxygen in the glazing clay. So it pulls it to the surface and volatilizes it, and that changes the color of the glaze. So in reduction, copper can turn it can also be green. It's a different kind of green, has a different quality of green than, it can be either a bright green or a dull green or a reddish green, depending on how much reduction. So it's also can do other things as well. You can get turquoise with it when you use barium or strontium. So turquoise is kind of between a blue and a green. And copper is another one, manganese, which we have one or two manganese glazes. The manganese glazes are poisonous, so don't eat them. And use gloves with your hands. So there's a couple of our glazes that are pretty, you have to be pretty careful with. But most of them are food safe. If you use the manganese glaze, I would put it on the outside, but not on the inside. And that's the saturated manganese that has a high amount. I think our blacks are safe. They have manganese in them, but or some. Maybe I took that one off. I don't remember. But I have a metallic manganese glaze. So nickel can get greens and blues and grays. How do you spell nickel?
Oh,
L-E? Okay. Nickel. What are some other metals? Chrome is another one. What do you think chrome will do? Chrome is a really weird color. I say weird because basically it's because it was very difficult for me to learn how to use chrome. What do you think chrome does? Whenever I tried to make a glaze without reading a recipe or I always got browns, dull browns with chrome. But if you have the right chemical mix, you could do chrome tint pinks, reds, raspberries, colors, really bright colors. I'll show you an example. This is a chrome tint pink, purplish pink. So that's a nice pink. That pink I don't mind. Some pinks are more like Pepto-Bismol. This one's a little bit richer. If you look close, you can see some variation in it. So this is chrome in the presence of tin. So if you put like 15% tin and just a little bit, like 0.5% chrome, it will turn pink. You can get darker colors by increasing the amount of chrome. So chrome will turn pink, but it will also turn red. Well, that's not red, is it? No, not red. Green is what I meant. So, and usually a bright green. If you get a good green from it, it's one of your brighter greens. So there's another thing that you can use to make color, and that's a manufactured product that already uses all these metals, and they're in a glass matrix so that they're stabilized so that they don't become volatilized as easily at higher temperatures or even lower temperatures. So they stabilize the glazes and they look more like the colorants that you think of when you're painting. So the things that you use to make colorants in paint are often the same chemicals that are used to make colorants in ceramics. So these are called stains, and you can put them in glazes, you can put them in slips, you can put them in clay. And the ones that we're using are mostly mason stains, but there are a lot of, and that's the company name. So, and stains, another word might be a spinel. That's an older term that was used. I have like one of the first books that was created for artists, potters, ceramic artists, studio artists in ceramics. And that's the Parliament, I think is his name, from the 1930s. And but later, there's a whole lot of good books out there on glazing. John Britt's one of the most readable. That's easy to understand, but not without its complexity in terms of how thorough he is with his explanations of glazes. So we use a lot of stains as well. They're stabilized colors that are made in a lab, and then you introduce them in up to between 5 and 10% is about the range. You can go lower than that and even higher than that, but higher than that it starts changing the glaze composition. Lower than that, you're not going to get a very strong color. And any of these, copper, iron, cobalt, or teal, so I would say 0.5 to 5%. You usually don't use more than 5% of any of them. 5% of some of these, like copper and cobalt, are going to be saturated and they're going to be really dark. Iron, you do that for dark colors. You saturate it. And iron is pretty innocuous. Any chemical is poisonous in too high amount. We have iron in our blood. We also have copper in our blood. We pretty much have all the minerals that we have up here. It plays some role in our even things that are generally poisonous. They're like minute quantities of these in our body. Almost every chemical that's in nature is in the human body in at least a small amount. Okay, so what's the last thing we got here? There's a lot more colorants. There's more that I can say about all of these columns, but I'm just giving some basic information right now. So an opacifier, what's an opacifier? What do you think an opacifier is?
Something that dulls the color?
It dulls the colors?
Or
yeah, to some extent. Yeah, like you would make, if you use some opacifiers with a colorant, it'll make it more of a what most people call pastel. But an opacifier, so if it's opaque, what is that in contrast to? Translucent or glossy. So you can have anything in a full range of something that is opaque, but still has a little bit of sheen to it. You can't see through it. It's not translucent. It's not transparent. all the way to almost a dry look. And then with glossy, you can have a range of opaque and glossiness. So most of the fluxes will cause a little bit of glossiness to the especially boron and lead and some of the others. But if you add zircopacks or zircon in different forms, that's one of the main opacifiers that's used today. There are some other ones. Tin is another one. Tin is used as an opacifier. Another one would be titanium. And titanium, I already talked about it with rutile. It's called titanium dioxide. There's a lot of other things that we could talk about too. Thank you. Okay, so any questions? Any questions? Just like you just already forgot it, right? So it took me years to remember a lot of this stuff, and I'm still using my notes. So as far as like materials, I can go in the lab and I can start playing around with them. I know what does what, and even without knowing the chemistry. See, the thing about glazes is you can have theoretical chemical formula for a glaze, and you want it balanced so that you don't have certain things leaching out of it, and the glaze is unstable and it changes colors over time. Because some glazes will do that if they're not balanced, or if they're fired too low. But you can have a stable glaze at low temperature, mid-range, and high temperatures. But there's like I said, there's a lot more that you could talk about. You can talk about crystallization. So one of the things that causes opacity as well is crystallization. So when you downfire in a reduction firing and in an oxidation firing, like in an electric kiln, crystals can start forming. Sometimes you don't want, sometimes like for cobalt, if you got too much cobalt in there, crystals start forming. They can also leach out, but they'll cause to refract the light so that it's no longer transparent. It may still be glossy, but, and there's some people that use this to even a greater effect to make large crystal forms on the surface of the glaze. So it becomes an actual like decorative motif in the glazing. And some people love that kind of thing. And I've seen it done well, and I've seen it done where it's just kind of, that's just kind of a gimmick to get people to buy it. But there's a lot of different ways to approach glazes. Anyway, so that should give you a basic idea of glazing. It's by no means exhaustive, but next class we're going to get in there and we're going to start working with materials. So when we start working with materials, you'll see more what, I may even ask you, what does this do in the glaze? So you can start thinking about it. Okay, that's it. Thank you. Get back to work, and I'll walk around and help you all.